The sixth example involves a curve with a saddle. Learn what this is here in differential calculus. How do we look for the critical points? Having a given function, take the derivative in order to have the slope. And from the highest or lowest points, the slope is 0. Equating the first derivative to 0, we can look for x. So to complete the critical point, substitute x into the original function to have y. Learning about the critical point, next is to categorize if it is the maximum or the minimum point. That is by looking for the second derivative of y, and then check if y double prime is negative or positive. If it is negative, the critical point is a maxima, or the highest point. And if y double prime is positive, then the critical point is the lowest, or the minima. We are to locate the critical points and identify if these points are maxima or minima with the given function. Note that x cubed is combined with the square of x minus 1, which says there are two terms, thus requiring derivation using product rule. So dy over dx is the constant 4 with the first term times the derivative of the square of the binomial x minus 1, then add to this the second term times the derivative of the first term x cubed. The derivative of the first term requires general power rule, making it 2 times the binomial x minus 1 raised to 1. Then by chain rule, attach the derivative of the binomial. From the second term, the copied part is the square of x minus 1, and the derivative of x cubed is 3x squared, with the derivative of x over dx by chain rule. Dx over dx is 1, which eliminates the derivative on that term. We then distribute d over dx among x and negative 1, where d of x with respect to x is 1, and the derivative of constant is 0. This simplifies the function. The equation then is further reduced into 4 times 2x cubed with the binomial x minus 1 plus 3x squared times the square of x minus 1. Expand the terms to take out groupings. So from the first term, distribute 2x cubed, making 2x raised to 4, minus 2x cubed. The expanded form of the square from the second term also becomes x squared minus 2x plus 1. Now distribute 3x squared among the perfect square trinomial and get dy over dx as 4 times 2x raised to 4 minus 2x cubed plus 3x raised to 4 less 6x cubed plus 3x squared. Collect similar terms to arrive at dy over dx as equated to 4 with 5x raised to 4 minus 8x cubed plus 3x squared. Take the critical points by zeroing out y prime, where 0 divided by the constant 4 still remains as 0. So the function is then 5x raised to 4 minus 8x cubed plus 3x squared as equal to 0. Factor out x squared from each term and get x squared with 5x squared minus 8x plus 3 as equal to 0. Applying the zero property of multiplication, we can equate x squared with 0, which gives x of 0, and this value is repeated. The other part of the function is also equated to 0, where by using the quadratic formula, the values of x turn out as 1 and 3/5, or 0.6. These are the x-coordinates of the critical points. The next thing to do is to look for the y-coordinate to fully locate the points. By using the original function, plug in the values of x to look for their y counterparts. At x equal to 0, y is then 4 times 0 cubed times 0 minus 1 squared, which makes 0. At x of 1, y becomes 4 of 1 cubed times 1 less 1 squared, which makes y as 0. The third x of 3/5 is also plugged in, making y as 4 times of 3/5 cubed times 3/5 minus 1 squared, where y3 is 0.13824. After identifying the critical points, classify them whether maxima or minima, and that is through taking the second derivative of the function. So y double prime is 5 times the derivative of x raised to 4, which is 4x cubed, minus 8 of the derivative of x cubed, which is 3x squared, plus 3 times the derivative of x squared, which makes 2x. Y double prime is then 20x cubed minus 24x squared plus 6x. Now plug in x of 0, making y double prime then as 20 times 0 cubed minus 24 times 0 squared plus 6 of 0, where y double prime is 0. At this point, the second derivative test fails. Before testing the first derivative, let's finish the rest of the coordinates. So, at x equal to 1, y double prime is 20 times 1 cubed minus 24 times 1 squared plus 6 times 1, making y double prime as 2. Being a positive, this means that the critical point is a minima. For x of 3/5, y double prime is then 20 times the cube of 3/5 minus 24 of the square of 3/5 and 6 times 3/5. This makes y double prime as negative 7.92, where negative means maxima. Thus, the curve's minima is at 1, 0, and its maxima is at 0.6, 0.13824.